Okay, so this is a little weird. We're going to try to talk about acceptance criteria for a building. We have an existing building. Come on. And so we're going to look at the data that we have from our utilities and see if we can't come up with some acceptance criteria. So the first set of data is this. This is therm data. And what we've got is we've got daily therms, natural gas measured in therms. So there's our daily therms number. This is the day that it occurs on. You see January 1st, January 2nd, January 3rd. Then we have some temperature data that comes in with that, the average high and the average low temperature for that day. So the first thing I did was I tested for some statistical relevance. I looked at the high temperature, so you can kind of see this is, is there, what's the slope and intercept between those two sets of data, and specifically what's the R squared? In this case, the variance in high explains about 55% of the variance in therms. The low is a little bit better. The variance in low explains about 60% of the variance in therms. And for energy data, for HVAC energy data, 60% is actually quite good. That's a decent correlation. So I decided that we're going to work with that. By the way, weekday and weekend, I just created a quick flag to see whether or not the usage was correlated at all to weekend or weekday, and the answer is no. So this is just a binary, if it's a weekday, it's a 1, if it's a weekend, it's a 0. And the averages between the weekdays and the weekends are irrelevant. They're about the same. So overall, this is the mean, 145 therms per day. Standard deviation 64, so tremendous variance there, right? Based on standard deviation, we'd say that 60 or 66% of the data would fall between two standard deviations, 128 therms, and then 99% of the data would fall between 3 standard deviations. It's a huge range, right? You can see the range is bigger than the mean, which is pretty radical. So we want to see if we can improve on that at all. And the way that I did that is I took the low temperature and I created some bins out of it. I found that when you're working with gross data, sometimes it's better to just accept that you're working with gross data. And so I rounded the temperature to the nearest 4. So you see 48 degrees, 40 degrees, right? 48, 56, 52. So round it off to the nearest 4. And once I do that, that clusters the data into bins. So I can look at, how many of these points actually fall into those different bins. It looks like we have a total of 567 observations here. But then I can look at the standard deviation and the mean within those bins. So for example, when it's 56 degrees outside here, and I'm picking one that's optimistic here, one of the better ones, my average is 102 and my standard deviation is only 28. So my standard deviation has dropped out quite a bit, which is to say that, that 56-degree outside air temperature is a pretty good predictor, or it narrows down our ability to predict the natural gas. So if our low of the day is 56 degrees, then we can expect our natural gas now to fall between the range of, well, 66% of the time it should fall between the range of 74 and 130. 99% of the time it should fall between the range of 45 and 159. And so based on that, we can set up some acceptance criteria here. And so here's what I've done. I've created this chart here where you have these outside air temperatures. And again, these are in bins. So you're only looking at 36, 40. So you round your outside air temperature, the low temperature of the day to the nearest 4. And once you do that, then 60% of the days, you should fall below this gray line here. That's our average plus 1 standard deviation. And then 99% of the time, you should fall below this second line here, which is to say that if you have any points above the second line, in the new system, you really should fail it. And then you're looking for 66% of the days to fall below this gray line here, this line that I've highlighted right there. Upper control limit is what it would be. We're not so much worried about a lower control limit, but we are worried about an upper control limit. So I started on natural gas because that one's a whole lot easier. Now let's look at the electrical. So here's the electrical data. We have, this time we have 15-minute interval data, which is quite a bit better. But what I immediately did is I took that and aggregated the 15-minute out to hourly data. And then I also, you'll see I took this temperature and I am going to put that into bins here. But let's start just by looking at the immediate relationships. So what's the relationship here between the kilowatt hours and the hour of the day? I also did that for peak. And then what's the relationship between outside air temperature and the kilowatt hours? And there is a relationship here. You can see there's a statistical relationship, but if you look at the R squared on that, it's only 0.33, which is to say that the variance in outside air temperature only explains 30% of the variance in kWh usage, right? And you can also very much see, look at the shape of this time of day curve. What I noticed is that the maximum seems to have a nice shape associated to the time of day. And so what I did is I took that and sort of looked at the data. So for every hour of the day, I'm going into the data and looking for the maximum that occurred, the maximum kWh that occurred within that hour of the day. And then I created this thing called use factor, which is literally just rounding or dividing by 5 and rounding it off. So a use factor of 7 equates to about 35 kW, whereas a use factor of 10 equates to about 50, right? And so I created that variable, use factor. Again, we're kind of taking what are these gross things and going ahead and accepting that they're going to be gross. Same thing with outside air temperature, similar to before. I rounded this to 4 degrees and created some bins based on 4-degree intervals. And we fall within those bins. And what you can see is this is, by the way, is the overall data. The overall kWh data has an average of 23 and a standard deviation of 12. And I can beat that standard deviation a good chunk of the time, right? Up until here, I'm beating that standard deviation. And then out here, I'm not losing a lot in terms of standard deviation. Maybe it's this 88 point. I am losing some, but you can kind of see that we're doing reasonably well. You could just set up some acceptance criteria just here, you know, based on if it's this outside air temperature, then my kWh's should never be higher than this. But I don't think that's correct. So what I did was I ran a linear regression model, and just to show you how to do that, if you're not an Excel guru, then you go over to data analytics, you run a linear regression model, and your linear regression. What I've done here is I've selected the kWh temperature as my y ranges. So my model is going to be x1 times a constant, x2 times a constant equals y plus an intercept. So this is the y data, the data that I'm trying to predict. The variables that I'm trying to use to predict that data are, well, you can't see it, but it's basically I've used this use factor and the temperature bin in order to try to predict that data. I'm not going to run this right now because I already did it, and it's right here. Cancel. It's right here. So what you get as the output of linear regression, a couple of key variables. One is you get this, how good is the model? And in this case, the model is in a multiple R of about 0.58, which is to say that the two variables in this model explain about 60% of the variance in the data. For normal correlation, that's terrible. But when we're dealing with HVAC energy data, I find that 50, 60% is pretty damn good. We're still going to have some very broad ranges, but that's actually not bad. And then to notice here, the standard error is 10, and that is in units of the model. So that's in units of kWh. What I can do then is I can, and this gives you those factors. So the y-intercept is -23. You multiply the use factor times 0.8. You multiply the temperature bin by 0.66, and then that's actually your model. I'll show you the equation of that model here in a second. So here it is, y-intercept, use factor, and temperature bin, which means that for any outside air temperature an hour of the day, I can then take the outside air temperature, put it into a bin, take the hour of the day, have that look up a use factor, just a lookup table. And then my model, which takes this y-intercept, this use factor, this temperature bin factor, and models out that at 35-degree outside air temperature at 7 o'clock in the morning, I should be using 6 kWh in the building with an upper control limit. 60% of my data should fall underneath 16.5, and 99% of my data should fall underneath 26.5. If it was 55 degrees outside and 2 p.m., then those numbers would change. And of course, based on that, we can actually create kind of a model here of acceptance criteria. And I'd recommend that we look at the hours, that 60% of the hours of the building, the kWh usage should fall below this model, right? Should fall below these predictions. If you want to see what this actually looks like, it's kind of ugly, but we'll go ahead and do that real fast. It looks like this. Sorry, how about that? No, that's pretty ugly. How about this? Don't like it. Anyway, you can see they're just lines. They're just lines going up. So at 100-degree outside air temperature, at 3 o'clock in the morning, our maximum predicted is 59. And at, here's my prediction in the afternoon, and then it drops back down to my prediction at night. So that, I think, is some acceptance criteria. So I'm sending this spreadsheet back, but I know that it's a horrible lot of data in here, so I wanted to create the video to sort of talk you through it at the same time.